Okay, let's start the class for section 1.7. So we have already learned all the methods in this chapter to check whether a series is convergent or divergent. Now I'm going to go over those methods in this class. Okay. So first example I'm going to discuss is the following. Okay, given a series n minus 1 over n cubed plus 1, we check whether this series is convergent or divergent. Okay, when you see this series, okay, first of all, you notice that all the terms are non-negative. Okay, all the terms are non-negative. So you can use the tests for some tests for series with non-negative terms. Okay. Now, I think the best way to solve this problem is use a comparison test, because I noticed that the nth term converging to 0. So you cannot use that to prove it's divergent. More likely it can be convergent. The reason is ignore the constant terms. You will see that this is almost equal to, the nth term is almost equal to 1 over n squared. Okay? But for this particular series, you can use a comparison test. Okay? So you see that this is going to be less than n, right? N cubed plus 1. And then you enlarge the denominator by drop the constant 1. Okay? After simplifying, this is going to be 1 over n squared. So we know that this is positive, okay? So we know that sigma n equal 1 to infinity bn. Okay? This is a convergent. Why it's convergent? By the P series test. Okay, P is going to be 2, which is greater than 1. All right, so now you show that Bn, sigma Bn is convergent. Then you conclude that this series An, okay, is convergent, okay, by the comparison test. I think be careful when you use the comparison test. You make sure this all the equality holds. Inequality holds. Now, if you're not sure, if you don't feel confident to get those upper bounds, then you can use a limited comparison test much safer. Okay, limited comparison test is going to be how to find the Bn. You still drop the constant terms. You only get n. You only got n, right? Here's n cubed, right? Then after simplifying, it's going to be 1 over n squared, which is Bn. I say you do not know, doing like that, you do not know An is less than or equal to Bn. But at least the limit, okay, is going to be, the limit is going to be 1, okay? It's easy to check that if you're doing like that, okay? Then the convergence of An is equivalent to the convergence of sigma Bn. So since sigma Bn, n from 1 to infinity, is convergent, you still have to say that why it's convergent by the P series, okay? A P series test. Yeah, P series test. Okay? Was P is greater than, P is equal to 2. Right? Then you conclude that this series is convergent. Is convergent. Okay. Now this time we have to say that by the limited comparison test. Okay. So you have slightly different ways to prove it's convergent, and other methods would be not useful. Okay. For example, if someone want to use a load test, or ratio test, and all the methods do not work. Okay, and the integral test maybe, but it's very complicated, so we don't want to use that. Okay, the second, yeah, whenever you see a polynomial over polynomials, do not use a ratio test. Do not use a root test, and trying to use a comparison test or limit comparison test to solve the problem. Okay, the second problem I want to discuss is this one. Okay. But this is alternating series. But before you apply the alternating series to prove it's convergent, okay, you cannot use alternating series test to prove it's divergent. Okay, first. You should make a simple observation. Does the nth term converge to 0 or not? Okay, so even you want to apply the alternating series test, you still have to prove that this term Bn, okay, converging to 0. But this term, the numerator is -1. Okay, yeah. So here's -1. Okay. So this this term may be decreasing, but at least it's not going to be convergent to 0. It's going to be convergent P1 as n approaches infinity. Why it's convergent to 1? You should see that, right? It's n squared in the numerator, n squared in the denominator. So if you really want to see why it's Bn convergent to 0, it's you divide by numerator divided by n squared and denominator by n squared. So this convergent to 1 minus 0, 1 plus 0, that's going to be 1 as n approaches infinity. So that implies the nth term. This nth term, the limit does not exist, which of course is not going to be 0. So by the n test for divergence, this is divergence. So then the series is divergent by the nth term test. The nth term test says that if it's convergent, the limit of nth term must be 0. Now it's not 0, so actually it doesn't exist because there is a negative sign in front of that. Okay, it jumps between negative and positive 1. All right, so when you see an alternating series, you're not necessary to use alternating series test to prove its convergence. For example, the next problem. Right? Sometimes it's divergent. Now this is an alternating series. Right? Is it convergent, divergent? Well, you have to look at this Bn. Right? Let's try to use alternating series test to prove it's convergent. So the question is whether Bn decreasing. I think it's Bn decreasing because the denominator is the exponential function. The numerator is just polynomial. So I strongly believe that this is going to be decreasing and decreasing to 0. Okay, but you have to prove that, right, before you apply the alternating series test to prove its convergence. So you have to prove, how to prove its limit, and where it's decreasing, right? So where it's decreasing, you have to look at the function x to the 4th and 4 to the x power. So we have to differentiate, right? Then 4 to the x squared, here's 4x cubed, and 4 to the x minus x to the 4th. The derivative of x 4 to the x is 4 to the x natural log of 4. Okay, and simplified. When I simplify it, I'm going to take 4 to the x out, and also going to take x cubed out. So I have a 4 here minus x natural log of 4. Clear, right? Yeah, I have an x. Okay. Clearly, this is going to be negative if x is greater than 4 over natural log of 4. Now, I really don't know, or even don't care how large of this number. If you really want to do some estimate, let me do some estimate, okay? Let me do, yeah, some estimate. So natural log of 4, yeah, what is natural log of 4? The natural log of 4, natural log of 4 is a number, 4 is greater than e, so it's less than natural log of greater than or equal to natural log of e, right? Which is going to be 1. So natural log of 4 is greater than 1. So that means 4 over natural log of 4 is going to be less than or equal to 4 over 1, right? Which is 4. So that means if x is greater than 4, then this is always negative if x is greater than or equal to 4. Okay, 4 is greater than 4 over natural log of 4. Okay, so that's enough. So that means, okay, Bn equals n to the 4 and natural log of no, not to natural, 4 to the 4 to the nth power, which is going to be decreasing for n greater than or equal to 4. Okay, I don't care the first few terms. Now this decreasing to 0. Why is this decreasing to 0? You have to look at the limit as x approaching infinity of f of x, right? So this is x to the 4 and 4 to the x power. It's the infinity of an infinite type, so you can use the repeaters rule. So I get 4x cubed and then 4x natural log of 4. And continue, right? And it's going to be 4 times 3x squared and 4 to the x natural log of 4 squared. Why you have the differential numerator and x cubed become 3x squared? The denominator, when you differential 4 to the x, you get 4 to the x times natural log of 4. So you have another natural log of 4 there, so it's squared. And then you continue. So you get 4 times 3. When you differentiate x squared, you get 2x. And here's 4 to the x natural log of 4 cubed. Okay, and then have to do the continue. You have to continue differentiate. 4, 3, 2, and 1. And 4 to the x natural log of 4 to the 4th power. Then you stop here. You cannot use L'Hopital's rule again because the numerator is constant. It's not a, it does not approach infinity. But clearly, denominator approaches infinity. The answer is 0. So the limit is 0. That implies natural log of n approaching infinity. Bn is going to be 0. Why? Because Bn is f of n, right? Then, so now you verify all the conditions required for the alternating series test. Therefore, this is negative, right? N minus 1 Bn. Okay, this is convergent by the alternating series test. Okay. Is there any better way to solve this problem? Yes, if you are misleading by the alternating series test, you can probably prove it in a slightly different way. Okay, maybe even I can get better convergence. So, so another way to prove it, it's much simpler. Let me repeat this this one. So maybe this is a Basuri's convergent. Okay, so this is my n, right? It could be negative. So I use this. Okay, take a look at the limit. Okay, the nth root. It's a root test. So look at the limit of the nth root. Okay. So the absolute of our n, the negative sign is gone. Okay. Then you the square root of the nth root of n to the fourth power is nth root of n then to the fourth power. And this just 4. Okay, the denominator is 4. So the numerator is going to be, the limit is going to be nth root of n, is the limit is going to be 1 to the fourth power. The denominator is 4, it's quarter. 1/4 is less than 1. 1/4 is less than 1. Okay, 1/4 is less than 1. So now we have, okay, so by the root test, we conclude that this series is going to be absolutely convergent, even better. Not only just convergent, it's absolutely convergent. Okay. So you can also use a ratio test to do that. Okay, to prove that it's absolutely convergent. You can try that. You can use a ratio test to prove it's convergent. Okay. So note. Okay. We can also use a ratio test to prove it is absolutely convergent. Okay. Oh, absolutely convergent. Okay. Right. You can try that by yourself. Okay. So as you can see that even it's not, if it is alternating series, it's not necessary to use alternating series to prove a convergent. Okay, you should put a note to that. Okay, in general, if the nth term contains n factorial, use a ratio test. Okay, but it's not always like that. So there's some examples. You have to use a root test, such as this example: n factorial to the nth power and n to the 4n. In this case, we really should use a root test because there's nth power here. Okay. Okay. So denote this by n. Okay. Nth root of n is going to be, right? So the numerator is just n factorial. The denominator is n to the 4th to the 4n divided by n, so just 4. Okay. So what is the limit of this? I think it is going to converge into infinity because n factorial grows much faster than polynomials. Okay, but you can also see that using the following argument: 1 times 2 times 3 times 4. Okay, that's right. It's harder to check, right? So we have n minus 3, n minus 2, n minus 1, n. Here's n, 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 n. Okay. So this is n to the 4th power. Now those terms converges to 1. But how about the rest of them? N to the 4, right? So this part converging to 1, no problem, right? That's easy to see. But this part converges to infinity because it's n minus 4th factorial. So clearly the the product approaching infinity as n goes to infinity, okay? So what does that mean? That means the limit of the nth root of n is going to be infinity. This is greater than 1. Therefore, this is the divergent. Okay, by the load test. Now, can you use a ratio test? I don't think so. It's hard to simplify. Okay. Okay. Well, let's look at this next problem. Right? Whether this is convergent or divergent. So look at the denominator. So my first concern is whether this is non-negative. It's always defined. Then I look at the sign n. The sign n, you know that the absolute value of sign n is less than or equal 1. So the smallest value of sign n could be taken is -1. So therefore, 2 plus sign n is greater than or equal to 2 minus 1, which is 1. So don't worry about the denominator. This also indicates, okay, it is also it's greater than, it's positive, but other side is greater than or equal to 2 plus 1, which is 3, right? So the denominator is always between these two. Therefore, it's going to be less than 1 greater than or equal to 1/3, okay? So as long as you observe that, then you see that the nth term never approaches 0. So this implies the limit, if it exists, it's not going to be 0. It's always between 1/3 and 1. So that means the series is divergent by the nth term test. Okay, so the series is divergent by the nth term test. So you should make a simple observation. First thing you have to look at, does the nth term approach 0? Otherwise, it's already divergent. Okay, so you don't need to worry about too much. Okay, just use the nth term test to prove that it's divergent. Okay, so how about this next term, next series? E to the 1 of n squared. Okay, when you look at this, you should know that the limit of e to the 1 of n is going to be e to the 0, which is 1. So the numerator is almost equal 1. But the denominator is n squared. So clearly, it is going to be convergent. But all I have to do is to look at the Bn, right? Yeah, find the Bn and then compare it with n. So the limit, yeah, after okay, then after simplify, you only have e to the 1 of n, which is e to the 0, which is 1. Okay, so if sigma Bn is convergent, then sigma n is convergent. But we know that sigma Bn can start from 1 to infinity. This is convergent, right? By the P series test. Okay. So by the Fourier test, right? Because this is a 1 of n squared, right? Bn is. So this implies n is convergent. Now, by the limited comparison test. All right. Okay, let's look at another problem. Yeah, here's another problem. It's an interesting problem. All right, so this series is going to be n squared e to the n cubed. What is the best way to solve, to prove it's convergent? This clearly it's convergent because denominator is the exponential growth function. Okay, it's an exponential function. The numerator is a polynomial, right? I think you can either use a ratio test. Why? Because it's e to a certain exponential function there. But that exponential function is quite different, just not e to the n. It's e to the n cubed. You can also try the ratio test. I prefer the ratio test. Okay? So the nth root of n, I prefer the root test. It's going to be one of n, right? And that is going to be n squared to the 1 of n. E to the n cubed to the 1 of n. So that can you simplify? Yes. Now the numerator get the 1 of n to the 1 of n, then square. I can switch the order. The denominator is n cubed divided by n is just n squared. So clearly it's convergent to 0. Why? The numerator convergent to 1. 1 squared. The denominator convergent to infinity. That's why it's convergent to 0. It's obvious. And that means the limit of this is going to be 0, which is much less than 1, right? Therefore, by the root test, it's convergent. So it is convergent by the root test. Okay, you can also use you can prove that use a ratio. The ratio is slightly more complicated, okay, than the root test. You can try, okay? All right, so let's look at next problem. Okay, look at this problem. Is it convergent or divergent, and how to prove it? Well, you know they are assigned to n. You don't know the sign, whether it's positive or negative, okay? But sometimes it's positive, sometimes negative. But we know that absolute assigned to n is going to be less than or equal to 1. So here we're going to do it. We look at the absolute value of this, right? It's going to be 1 over 1 plus 2 to the n. But this one can even change it to this, okay? And that is our Bn. Clearly, sigma of Bn n start from 1 to infinity, which is going to be 1 over 2 to the power m. This is a convergent, you know why that, right? Why? By the geometric series test, okay? Geometric series test that it's convergent if I is less than 1. Absolute value is less than 1. Here I is going to be, it's going to be 1/2. So remember this, okay? Remember this. This is going to be r to the n, okay? This is going to be convergent if and only if x is absolute value is less than 1, okay? Otherwise, it's divergent. Okay, this is a geometry series, a fact. Okay, you're using this fact. Okay, so now, so this implies, you cannot directly say this implies and the absolute value of this term is convergent, right? Okay, this is by the theorem. Right, this theorem says that if the absolute, yeah, no, this is actually not. This is just by the comparison test. Okay, by the comparison test. Then you conclude that this is the absolute convergent or just convergent. Okay. Is there any other method you can prove that? No. You have to look at absolute value, which can because it's really hard to understand the sign of the numerator. Okay. So let's do the next problem. Okay, now this is very complicated term, right? It's positive, it's good. I think both numerator and denominator is almost a polynomial function, so just need to look at the leading term, okay? So let's look at the leading term. Okay. This is going to be take n to the fourth power, right? It's a 1 plus 1 over n to the fourth power. So you can also take n cubed out, right? So it's 1 plus 1 over n squared now. So actually, you will get n squared here, then n cubed here, right? And this is going to be square root of 1 plus 1 over n to the fourth. All right, so this is almost equal to n squared over n to the n cubed, which is 1 over n. Let's call it Bn. Yeah, it's easy to check the way you can calculate the Bn. Guarantees the limit is going to be 1, okay? Always. Okay. But this Bn is divergent. This is a harmonic series. It's divergent. We know that. You can also say that by the P series test, and P is going to be 1. Okay. So that implies this complicated series is also divergent. Okay. By the limit comparison test. Yeah, limit comparison test. Yeah, because Bn is just harmonic series, kind of divergent. But An is almost equal to Bn, right? Equal to 1 over n. Of course, it's divergent. Okay, so the last problem I want to discuss here is this is difficult because you don't know which term you're going to compare, and you don't know how to combine those two terms. There's no way you can combine it. Okay. Right? 2 to the 1 over n minus 1. But I know that 2 to the 1 over n, limit when n approaches infinity, it's going to be 2 to the 0, which is 1. So that implies the nth term it's going to be 0, but I don't know how fast it decay. Right? I don't know how fast it decays to 0. But let me try. Okay? Try this ratio. Right? It's going to be 0 or not? In order to prove that, you have to apply, which is, I believe that it's going to be, I claim it's going to be nature log of 2. Okay, why? So look at this limit. Okay. Okay, this is you can use a L'Hopital's rule. Okay, it's a 1. Why it's a 0 over 0 type. So its derivative, the numerator is going to be 2 to the x nature log of 2. And this time you cannot apply the L'Hopital's rule. So they're actually just equal to 2 to the 0 nature log of 2, which is nature log of 2. So we get the limit. Okay. So that proves this limit. Okay. So that means you find you compare this term with that means this n, the nth term, is almost equal to the bn, which is 1 of n, right? Right? So the limit of n over bn is going to be 1, as just showed above. But so I know that this is going to be divergent. You know why it's divergent? By the p-series test. With p equals 1. Okay? So therefore, this is divergent by comparison test. Limit comparison test. Okay? I think I did all kinds of problems in this lesson. Okay? So I stop here and we will continue review these problems in the review classes. Okay?